Dr. Karsten Nohl.
Thank you very much. We thought we ran out of research topics in our research mission of warning people about outdated security, and others and ourselves who went through all the old systems from the 80s and early 90s, found proprietary crypto, broke that. This time we looked at an application where we didn't think we could find quite as much because it's much newer, much more modern, still kind of having its use potential in the future, not so much in the past. And it's built around standard cryptography. So these are SIM cards. However, we did find quite a lot and want to share this today. Not just the research results, but also a little bit of story around the responsible disclosure, which I think is pretty unique, at least as far as our research are concerned, that we're looking at a problem here that was not just found and discussed openly, but also in a lot of places fixed quickly. And at least in my research world, that usually doesn't happen. So all right, SIM cards. Originally invented to create a link between a phone and a contract, so that the charges are billed to the right person, also that the right number rings at the right phone. So it was the bonding between the handset and the number and the charges. Since then, though, this is more than 20 years ago that they came up with the SIM card, it has been heavily extended. First by simple functions for older phones, like storing text messages, storing the address book, things that didn't fit on phones back then, apparently. Today, these functions are still there, but rarely used. However, the SIM card keeps growing through Java software. And pretty much every SIM card for the last 10 years or so was able to run Java software. And not just the Java software that it came with from the factory, but also new Java software that you can download in form of apps. So these are not apps that you would go to an app store and click, I want this, but rather apps that somebody else says you should have on your phone. And it's pretty much outside of your control what is running on the Java. So it's the operator dictating that. And uses that are popular in the wild are, for instance, roaming management, where your network operator may have preferential pricing with some networks in the country, but not others, so that the SIM card steers your phone to use certain networks and not others. You'll notice that when you're traveling, that your phone always wants one network, even though you're allowed to also use the others. In the developing world, also payment is a popular SIM card application. I hope nobody gets seasick. I couldn't look at this very long. Payment is very popular. Africa, for instance, some countries do the majority of banking through mobile instead of retail banking, so that they never really had retail banking, and then mobile came around, and now they're happy with that. It's coming to us slowly too in the form of NFC payment tokens. So also the European or developed countries, SIM cards will become payment tokens. That has been coming for a long time, and everybody expects it to be here any moment, but they have for the last 5 years that too. So it's heavily extensible, and what the future brings, nobody can tell. But for most everybody, these functions lay bare. You don't notice that something useful would happen on the SIM card. However, even though you don't get the benefit out of it, you do incur risk by having this, and that's what we want to discuss today. Few words on what we are not going to discuss today, because SIM cards are a large collection of security functions. So some that we won't cover are the PIN codes of breaking this 4-digit PIN code. No interest in this. In fact, the attacks we're doing are completely outside of what's protected with the PIN code. So that's a different part of the SIM card. Neither are we concerned with the authentication function. Some of you may remember the COMP 128 hacks from 6 years ago. So those were also an attack on a SIM card, but on a function, that's this hashing function, that we're not concerned with here. Neither are we concerned with the smart card security. Every SIM card is a smart card, and of course that brings a lot of protection. There's good talks, for instance, by Kristanovsky, where he shows how to break a smart card. So this is a lot more effort, something like a few weeks in a well-equipped lab. But then, of course, through that you get access to the SIM card. Would like a much faster and easier way, especially one that's non-destructive. So in this talk, we're concerned with Java software as it's running on the card and as it's being deployed to the card, with the protocols that facilitate that. All right, and we want to concentrate on these two things. How does Java software get put onto the card, and how can we possibly abuse that? And then once it's on the card, what can it do, and how can you possibly elevate the privileges that it has, kind of routing the card. Sounds good. All right. So these protocols that are used to deploy Java onto the card, they're called OTA, over the air, and they work by sending text messages of a specific format. So these are not text messages that the user would ever get to see. They are specified as the handset must send them directly to the SIM card, and pretty much every handset does that. So this is universally supported by phones. Don't inform the user, just put it on the SIM card. And for things like roaming management, that's probably advantageous. The user doesn't want to be buzzed with all that management stuff that goes on in the background. There are security functions that are commonly used. You can both require cryptographic signatures. So this is MAX, because this is symmetric key crypto. As well as encryption, again, symmetric key crypto. And most every card that we have come across requires signatures. Some cards, in addition, require encryption. A few cards only require encryption. And if you think about, since it's symmetric anyway, it doesn't make a big difference whether you use encryption or signatures, as long as the commands are well formatted. So the communication is facilitated through these SMS that are then encrypted and or signed. And the keys that are used, as well as the security level that is required for this communication, is burned into the card at manufacturing time. So you're not supposed to change anything about this. In particular, you're not supposed to change the use of the encryption algorithm later on. And a lot of manufacturers, well, network operators, I should say, choose the worst of three choices. So among AES, triple DES, and DES, they go with the 70s era DES algorithm. Nobody really knows why, and if you ask them, it's just kind of a legacy thing. And in fact, even when you ask the people that wrote these standards, they don't really remember why they put DES in there at all. So this was specified at the end of the 90s. And back then, most everybody has already moved away from DES to triple DES for kind of backwards compatibility with older hardware, or to AES predecessors. It wasn't standardized back then yet. But people already knew how to build better, faster block ciphers than triple DES. So somehow it snuck into this standard, and we find that about half of the world's SIM card use this very old standard. Sometimes in a mix with newer standards too, so every card can have different keys of different security levels, but of course, weakest link security principle applies, so whatever the weakest key is makes the card vulnerable. The use of DES would allow for an attack that where, let's say, you passively intercepted one of these messages, you could brute force the key, right? An academic attack may be practical in a few circumstances, but certainly limited in two ways. First, you got to wait for some OTA communication to happen. probably your best chance is to hang out at an airport, for instance, where a lot of roaming management will happen to phones that just landed in a new country. But it's still, you're gambling, and you'll get random people's OTA messages. Secondly, to brute force a desk key, even though it has been shown possible many, many times before, still expensive. The first machine to do it was DeepCrack. That costed $1 million. Today it's cheaper, but still perhaps at a price point where you say that's not worth it for breaking SIM cards. So we want to lift these two limitations. The first limitation being that you have to wait for OTA to be sent by other people. Here's a way now to force the card to send you OTA text to work with. And this is what used to be a gap in the specification. They fixed it by now, but even new cards don't necessarily implement the new standard always, where they didn't specify what happens when you receive a wrong command, or a correct command with a wrong signature, I should say. Right? Some cards just ignore that. They say the signature didn't match, I'll throw this away. Some cards respond with an error message, and some of these cards sign the error message. Right? Perhaps thinking that if they didn't do this, it would allow some form of denial of service against the OTA server, because now everybody can send error messages unsigned. So the behavior differs. And when they do send a signed error message, that of course is now a message that you can break the key from. Right? And about a quarter of the SIM cards that we tested over the last couple of years have this behavior, and we also measured it at Ohm with y'all's help, and we'll come to those results in the end. And it seems that our sample set definitely holds up. So that lifted the first limitation. Now you can, just given a phone number, find a message to work with, right? You send a wrongly signed message to the phone, and it may respond with a signed error message. Still, you have the second issue that you don't want the $1 million machine, or rather, today it would be €50,000 for an FPGA cluster that breaks a desk key in one day. Still, maybe not worth it. However, you could, if one condition holds, compute rainbow tables. Right? The very same thing we computed to break A51, another cipher with a too small key used in phones. So the desk key is 56 bits. Brute forcing it takes a day on an expensive machine. Pre-computing it also takes a few brute force cycles, but you'd only have to do it once. Pre-computing, though, relies on the property that the message is predictable, that you can force a phone to sign a very specific message. And each phone should please sign the same message, because for this message and only this message, you pre-computed the tables, right? So let's look at the communication as it's happening and investigate whether the attacker can actually get a known chosen response. So the query simply states, this is a binary SMS through some header. So this is the type that the phone knows to send to the SIM card. It specifies the security, both the security that it uses. So this, for instance, says I don't use encryption, but I put a signature on it, and it also specifies kind of as a wish list what it would like for the SIM card to respond with. And it says also you should not encrypt, but please sign it and send it anyway, even in an error case. So not all SIM cards honor this bit, but those that do that then give us plain text. It says which key should be used. So there's a couple of different keys, and you may need to kind of brute force them through several SMS. Not all of them may be vulnerable. It targets a specific application. Each of them can have their own keys. And it includes a signature, of course, the wrong signature. We can't compute at this point the right signature. The card then responds, again, as a binary SMS, includes, again, the application number. It includes a counter. This is meant as a security feature against replay attacks. Fortunately for this attack, the counter is only checked after the signature is being checked. So since the error code says the signature is wrong, the card never got around to checking whether the counter matches, and it just copies the counter from the response. And the response itself is this error code. So 5 fields, 1, 2, 3, 4, and the 5th at the end, are either chosen or static, and only those go into the crypto signature. So somebody can choose the entire message now, and then compute the rainbow tables. Right? So it's a lot of design decisions influence this here, that now it's not the $1 million machine anymore, but it's a single computer to break one of these keys. And before I explain how that actually works, let's actually start doing that, because it takes sometimes a minute longer than I would like for this demo. And let's start by collecting signatures from one of these cards. So I'm not going to do this over the air. That's pretty unreliable. And in fact, a lot of networks also started filtering these queries by now, kind of firewalling from the attack. So we'll do this passively, but using the exact same messages I would be sending over the air. Let's see, this tool I want. The font size, yeah. Let's see, how do I do this? Command plus, alrighty. So that broke it a little bit. Basically what this does is it sends, SMS. It pretends to be the phone, and it sends, those SMS that it received onto the SIM card, and then sometimes the SIM card responds with a cryptographic signature. That's what you see at the end. Sometimes it doesn't. And this goes through, as I said before, kind of brute forces the different keys, at least the first 6. There's actually more, but in our experience, they're never really used. And it uses a few different messages. So actually, we run a few different attacks in parallel here, just because there's different error codes sometimes coming back. For each of them, we need our own rainbow table, though. So, and then we take one of these cryptographic signatures, and then run it through a cracker. All right, submit. Let's see. So this is now going on in the background. It may take like 2-3 minutes. Sometimes it's faster. Let's come back to this in a little bit. Let me explain in the meantime what's happening here. What is a rainbow table? Rainbow table is an optimization on a code book, and a code book is when you compute a secret mapping for every possibility and keep a record of it. It's kind of like the phone book, right? If you consider the mapping between a person's name and their phone number to be a secret operation, it's simple to go one way by calling them. It's pretty hard to go the other way, right? Unless, of course, you call everybody until you hit the right person. That's brute force. But while doing that, you can write the phone book, right? Because then you know everybody's phone number. And that's exactly the simplest time memory trade-off point, where you spend a lot of space, phone book pages, but little optimization. And in fact, with a single lookup, you can then find everybody's number. Now, doing this for 2 to the 56 entries is petabytes in size. So this may not be an optimal attack unless you have infinite hard disk space. There are other trade-off points, though, and that's where it gets interesting and gets into this discussion of rainbow table. So instead of just having a 2-column data set, you have a multi-column data set, and they are linked through, in this case, the DES computation. So you start with a random value, and you compute DES on it. You treat this as a key again, and compute DES, and treat this as a key again, and compute DES. The plaintext is always the same, right? We predicted the plaintext before. And this data set also it's kind of like the phone book, only a little bit more complicated. But let's assume the same values are covered in this entire data set, of which then you only keep the first and the last column. The rest you throw away. And if this, like in our case, is 32,000 links, then you only need, I guess, 16,000 of the storage, right, of original. So then you come from petabytes to terabytes, much more manageable, just cheap hard disks. However, the lookup, of course, now is more complicated. It's not a simple look into the phone book. Instead, you have to do some more computation. So let's say you observed this value as a signature, 2F06. You try to find it in your data set, and it's not there. You didn't store this value. So what you do is you compute the des function on it, right? Kind of working your way backwards into the set. You again look into it, still not there. You compute the des function on it again. Now you find it, right? In this case, because it's 2 links from the end. You find it here, you know what chain it belongs to, and if the public value is in the chain, the secret value is also in it, just one step before. So you recompute the chain up to this point, and you got your secret. Right? So that's the simple time memory trade-off. Now in this super simple case, it doesn't actually work very well, because as you can see here, sometimes values collide, and then you generate a lot of redundancy. Chains become more and more similar, and if this is terabytes in size, most of it will be redundant. And that's where people came up with this idea of now rainbow table, meaning you use a different color in each iteration, and this color can be as simple as an XOR of a static value. So this would be the des computation still, but XOR 1, des computation XOR 2, XOR 3, and so forth. Now if you have a collision here, and it's not exactly in the same column, you don't generate redundancy so much. Right? So that's the optimization we needed to do to achieve any reasonable coverage with this. And our data set is still not perfect, something like 30% coverage, but as a proof of concept, it certainly works well. So let's go back here, and this actually does say cracked now, so it did find a 56-bit key here, right? On a standard computer, not this computer, but one back in Berlin, in however long this took now, a few minutes, right? So that's the first, that's the cryptographic optimization that now, at least I think, moves this into the realm where everybody could be attacking SIM cards, right? The cost is very low now. All right. Everybody good on rainbow tables? Everybody got the concept? Right? So time memory trade-off. You spend a little bit more time now than with the code book through all these computations. In fact, quadratic, so that's what moves it into minutes, but you can store it on a simple computer. Oops. So yeah, let's skip this because I've already shown you how to catch the signatures. What I'd like to discuss now for just a minute is how some of the companies responded to this research, some of the network operators. So I should say before that a lot of them responded very constructively, but still some shrug it off a little bit too quickly. One of the American operators, for instance, publicly said to the press, we didn't even look at the problem, we know we're not affected. And I think that's a little bit too fast. So here's 3 things that the operators came back with saying. Some of them point out that they don't even require signatures, so this attack wouldn't apply. Instead, they use encryption, right? And both is DES CBC, so it really is a replacement. However, that actually makes the attack worse, because more cards respond with an encrypted error message when you ask them than with a signed error message. So, and the only difference now being that you'd have to compute a different rainbow table, because now you're not predicting the crypto signature anymore. Now you're predicting the encrypted version of it, right? So whichever operator said that, now they should go back and check the exact configuration. Others stated that they don't use OTA at all. Well, good for them. However, their SIM cards do, and even if you as an operator lost your keys, they're still there and crackable. So in fact, I think that may make it a lot worse because you may not even have changed the key from factory keys. You may never have considered updating to a newer encryption standard. So those operators certainly also need to go back and do a little bit more homework. Now, the third case is the most interesting because it actually follows what we would recommend them. They say, we have triple DES, we're not affected. Now, some of them forget that, of course, they only changed over to triple DES, let's say, a year ago or two, and many SIM cards are older. But even if they had triple DES for a long time, they could still be affected. And that's for at least 3 reasons. There's probably more ways to screw this up. Some operators changed from DES to triple DES on the cards, but not in a database layout. So they still only have 56 bits to store a key, which either means they use 56-bit and then pad it with zeros, or they use the same 56-bit key multiple times, right? And if you do, so there's two variants of triple DES. There's a 2-key variant and a 3-key variant. If you use the 2-key variant, at least you get something different if you use the same key twice than what DES would look like. But in a 3-key variant, it's encrypt, decrypt, encrypt. So if you use the same key, they just cancel out. And one operator, at least, was very confused when we told them we could break it with our DES table because they thought they were using triple DES, but they have downgraded it automatically to DES, just spending more time computing the exact same thing. Some operators did not change their standard keys. So a triple DES key that is a standard programming key, for instance, would be 0A, 0A, 0A. That's not very hard to crack. And then some cards, this is only on very specific cards, are attackable through a downgrade attack. I kind of stumbled across that by accident too. It's also something that the standard is not so super clear on, but everybody who thinks about it for a minute sees how stupid it is to not implement it the way where downgrade isn't possible. So what's a downgrade attack? It's where the card is kind enough to sign error messages, whatever you requested to sign it with. So if you say, I sent you a DES, DES signature, and then the card says, no, your signature was wrong, and it signs that with DES. If you send it a triple DES signature, it again signs the error messages with what you chose, right? You still need to break the triple DES key. It will not accept anything unless it's triple DES signed as correct. However, now you can crack these in portions. The key is stored in the memory as 3 different 56-bit values. And when you specify an algorithm that uses a shorter key, it just takes the first part of the key. Right? So we already know how to break a 56-bit key, the first 56-bit key. That's through the signed error message, look it up in the rainbow table. The second one now would be signed with a 112-bit key, right? So that's too hard to brute force or to build a rainbow table for. However, since the first 56 bits are already known from the earlier attack, the entropy collapses to 56 bits at most. So you have now a brute force attack on 56-bit, and even the last one where they really used the state-of-the-art 3-key triple DES, again, becomes a 56-bit problem, right? So I need to emphasize, this is only on few cards from certain manufacturers, but still, whichever operator said we didn't even look at the problem, we are not affected, they better look at this before they conclude. So downgrade attack on triple DES. So to summarize this first part, cards are affected when they're responding to a wrong signature with a cryptographic signature, not just zeros in the signature field, but actually valid signature. And if they either using DES, then they're affected directly, or when they're prone to this downgrade attack, then they're affected a little less severely, because now somebody would actually have to go through 2 brute force cycles instead of just computing a rainbow table. But so all in all, somewhere between 500 million and 1 billion cards we estimate are affected by this, fall into this box, right? So it's not everybody's card. In fact, it's just a small percentage because there's billions of cards, but a small percentage of billions still is a large number. Everybody good so far? Then we move into the second part now, to see what a let's call it a virus, a Java virus on the SIM card could do. Now you crack the OTA key to sign viruses, and you can deploy them again through SMS, probably more than one SMS, but these are you can basically send arbitrary lengths Java onto the card, and the card exposes certain functions to all Java applets that, of course, the virus can abuse. Included obvious things like sending SMS. That's how an applet would usually communicate with its server. But also included are functions that where it's not all that clear why a SIM applet would ever need to do that. For instance, dialing a number for you and then sending DTMF tones. That's very useful for a virus that wants to log into your voicemail and reconfigure things or forward messages. Not sure where else it would be useful. USSD is asterisk 100 hash, these shortcodes. It's also used by some SIM applets as a more reliable communication channel than SMS. USSD doesn't get buffered somewhere and maybe delayed. So it's clear why it's on there. For abuse, it would allow you to, for instance, change the voicemail number and redirect all calls. Perhaps if you do it smartly, you'd redirect it, but then again redirect it to the original number, so you sit in the middle. You have to switch off the redirect quickly, though. So it's a timing exercise. The SIM card, for whatever reason, is allowed to ask for your GPS coordinates and then send it through silent SMS to whoever is asking. Supposedly in some countries this is actually used, and people are regularly tracked. But again, here the virus can abuse this. And then the most interesting one that I've never seen in use is the SIM card can ask your phone to open a URL in the browser. And of course that allows for all kinds of interesting attacks where you ask the user to install an app or spoof a banking website, anything like that. So these are all the functions that are exposed to any Java and that are accessible no matter what. There's other data on the SIM card that should be protected. For instance, the master key, this KI key, from which all the other cryptographic keys derive that protect communication. So GSM, UMTS, LTE, everything is protected by cryptography at different security levels, as we know, and all of this derives from one master key. So that would be a very interesting key to steal, as are some other items on the SIM card. But since this is Java software, it should really be constrained to its own memory space through sandbox. And building a sandbox should not be all that hard, one would think. However, those security companies that build SIM cards apparently fail at even this basic exercise. I should say again, some of them, right? Not every SIM vendor is equal here. But the main two are and equal in the sense that they can't implement Java sandboxes apparently. So through some queries that are basically just exceeding array bounds, but in less than very straightforward ways, the Java is allowed to read anywhere in memory and even write anywhere in memory. And the construct, we're not disclosing exactly, we're still in responsible disclosure. The construct has to do with multi-dereferencing. So if you just give a simple integer, or I guess short in this Java world, to the a too small array, if you exceed it, that is checked and you get an exception that says, well, you're trying to read a value from your array that doesn't even exist. It exceeds the bound. But if this value is fetched a little bit more complex through multiple dereferencings, apparently the check doesn't happen anymore. And then you're allowed to read and write anywhere. So meaning you can, for instance, steal this master key, right, to decrypt all communication. you can read any other Java process that also lives in its little sandbox, but now you're underneath all of this. And really break into any security they may come up with in the future, because now you're on the operating system level. And to show what's then possible, let's see, so we cracked this key, we deployed the virus. The virus read a very specific part of memory, that's this KI key, and that allows us to basically emulate the card. So I have a phone here that has no SIM card in it, right? But also I have a little piece of software that emulates the SIM card entirely from this stolen KI value. And let's see. So this is now using the Osmocon software that's very popular for a whole range of attacks on GSM. Let's see. So now this should be logging into one of the Dutch networks. And then we can, use it as a normal phone. This step sometimes takes a long time, so let's be patient for a few seconds. Yeah, these phones, they used to be a few euros on eBay. They've gotten up in price every single year, right? But they are very useful. Yeah, let's also come back to this in a minute or so. Not sure what exactly it's negotiating here. So to summarize the attack and what I'll show once this logs in. Against a certain percentage of SIM cards, and at least a couple hundred million SIM cards, somebody can, just given a phone number, send commands there, get stuff back, run it, a few minutes through a rainbow table, have a key with which they can sign Java software, download the Java software onto the card, already do a bunch of abuse, like, send SMS to expensive numbers, but also then further dig into the card by breaking out of the Java sandbox and read and write anywhere in the SIM card, to the point where you can do a full SIM clone. Yeah, thanks. Let's restart this, because I'd really like to show you the cloned SIM. Now, we'll come back to it in a minute. Sorry, demos are always a little bit of a risk. Let's discuss just for a brief moment what network operators or others can now do to prevent this type of an attack. The obvious short-term thing to do, of course, is to filter these very strange messages that the attacker is exchanging with the phone. This should not really happen, that two phones exchange these management messages. They should only ever be sent between phones and the OTR server. Right? But even that's a little bit complex, because how do you know what are OTR servers of, let's say, other networks for which you have to hand down the OTA messages to their roaming users? So as a short-term solution, a lot of networks have actually implemented this already, which makes it harder and harder for us to research this or even demo it over the air. So when we tested this morning, probably the Dutch network actually filters what we're trying to send to Germany and get back from there. Sometimes they overfilter a little bit. So for instance, roaming optimization in one big European country doesn't work right now, so they really filter everything. In one instance, even FaceTime stopped working, because when you try to start Apple phone video chat, they send a specific SMS of a different type, so this shouldn't be caught by the filter, but they definitely over-filtered significantly in a few cases, and maybe now it's swinging back. Some networks don't yet filter, so it's all over the place. However, no level of filtering is for instance, going to prevent IMSI catcher-based malware installation, right? So when you just start a fake base station, and there's a couple around here too, I noticed, that of course then circumvents any type of network level filter. You talk to the phone directly. Same with a virus on the phone side, let's say an Android virus, that can of course speak to the SIM card directly if they wanted to, maybe put the rootkit a little deeper than Android side. Operators are encouraged, and some of them are doing it already, to find more long-term solutions. And one long-term solution, especially for those operators that don't use the OTA much anyway, would be to just deactivate it. In fact, on some cards, you can do that yourself by sending too many wrong signatures to it. Eventually, it'll stop responding. It has an error counter in it. And just 6 or 10 is usually enough. So some operators actually did move to deactivate OTA, and then probably will then replace cards eventually, or hope that you replace your card when they come up with the next form factor and the next form factor. So now people are kind of pressured more into using newer cards. More elegant solutions, however, reconfigure the cards, and this is probably my favorite part of this entire research, and I only really realized how they do it like a week ago. So the standard very specifically says you're not allowed to change your security settings, probably thinking that otherwise people could do downgrades of the security setting. But this time they want to do an upgrade from DES to triple DES or AES, not allowed, very specifically. So to do it anyway, what at least one operator has done is they put a Java applet on the card that then uses the sandbox exploit to hack into the operating system and rewrite parts of the operating system, right? I think that goes a long way in showing how good industry can be at adopting a hacker mindset. And I didn't think they would do it this way, but yeah, apparently that's what they do. Now, ironically, of course, those cards that don't have the Java bug, so that only have one bug, they don't get to patch the one bug. They're lacking the second one. So sometimes it helps to be double vulnerable to then prevent the worst vulnerability. And then, as a perhaps complementary long-term solution, I think phones should really give users more control over these OTA messages. Every baseband could possibly filter these messages too. The phone doesn't have to, from strange sources, hand down SMS to the SIM card, but it does, and it gives you absolutely no control over what's going on. Very, very old Nokia phones, they still ask you, do you allow the SIM card to respond to some strange SMS? And you could say no. I'd like for this feature to come back and to at least have some way of modifying it, perhaps in Android. Right, so okay, so this actually finally logged in. So it's connected with Vodafone now, but it has nothing to do with Vodafone really. It's a roaming card. So let's try to call myself. No prank calls, please, on this number. Oops. So, and this looks like this is ringing. So I'm trying to hide the phone number so they don't deactivate this card. So this phone with no SIM card is now calling me based on a cracked KI key. Oops. Thank you. All right. So some operators already moved to preventing this. Others are lagging a little bit behind, but hopefully will do so too soon. We estimate that somebody who really wanted to put all these pieces together would take 6 months. So we took 3 years, but of course now we already said where to look and what tools to use. So in 6 months there could actually be criminal abuse of this. So this is plenty of time for all network operators to come around and fix these bugs. Perhaps by exploiting their own cards if that's what it takes. We did actually think that by now already a lot of cards would have some of these bugs disabled. My colleagues here for the last 3 days and today again ran a workshop here to test cards, and many of you came and thank you had your cards read out by us. And we did think that we would now observe that a lot of cards already did get fixed, like with the networks that we're in close touch with. But that doesn't actually seem to be the case. In fact, your sample set, of course not representative, but so those cards that we did sample actually give out more plain text than the cards we collected over the last couple of years. And this is even though some of your networks will already have fixed this. Right? So it seems that currently the networks are heavily focusing on filtering, but not many are doing something to the card to improve it yet. So during the same workshops, we also found yet another issue that we hadn't been aware of, and that is terribly chosen keys. So here, just a couple of example keys from cards that we broke over the last 3 days. So you see this key, how it has all these zeros. So this has at most 16 bits of entropy. So there's 8 ones in it. So you'd think that they flipped a coin 16 times. That's breakable even on my laptop in a few seconds, right? So if you have a terrible entropy source that generated this key, moving to AES, for instance, does not help. Right? So a lot more cards could be affected once people start specifically looking, for instance, for weak keys. And this was not an isolated case. So you see how all these keys actually fall short of their 56-bit entropy limit. So this one could be just a sampling variance. It could very well be that this is 56-bit, but all of these are clearly fall way short of the mark, right? So we hope sincerely that this is not, the research that broke SIM cards and then they got fixed. This is the research that starts a whole research field of breaking SIM cards in a lot of ways, and I think this would be an interesting avenue here. Few words and then I'm done on responsible disclosure. And we don't usually talk about this very specifically because it's the same old story almost every time. You publish research results, industry tries to talk you down, criminals find it more interesting than industry. Criminals actually do it. Industry can't talk you down anymore, they fix it eventually. Not this time though, at least for those operators that were open enough to start this dialogue months ago already. So we've been in many months of responsible disclosure now, and found that everybody is working very hard for this to be fixed. And I think the hacking into their own cards to fix them goes a long way to showing the mutual respect, right? Both from us that we respect them and don't want to hurt them too much if we can prevent it, but also they for our methods and our results and our ambition to actually make it better by making it worse in the short term, right? By showing the problem and then fixing it. Interestingly enough, the sentiment in the industry this time didn't have to be convinced first. Usually when we finally talk to people, it's after we told a lot of lawyers, leave us alone, we're not going to sign an NDA, just accept this as free research that you can use, but don't try to get us into your machine. This time they didn't even try. And I think the times have changed a little bit. I think that it definitely helps that no company now wants to be responsible, for the NSA hacking into your phone, right? I want somebody else to be responsible for that. But also I think what helps in this case is that it doesn't just affect the privacy of potentially everybody, it also affects their revenue streams, right? So they focus on something where they can lose money. Ironically, all the other research we have done in related areas, like the A51 research, these things have not been patched yet. So we have 4 years worth of results, of which only the most recent has been fixed in record time. Right? So perhaps we need to find a way of creating criminal business cases around these other attacks that would actually hurt them financially for them to change. Right? On the right-hand side here, just for future reference, a few lessons learned from our interaction with industry, and I hope this research was motivating enough so you do get to break your own SIM card, find new ways of doing it, and once you do, perhaps this helps you, work constructively with industry to fix this. It's definitely very, very rewarding for us to see how much change we already initiated, and so overall a great research project that I think helps everybody in the end. Well, with that, thank you so much for your attention.
I'm afraid we don't have time for Q&A after the sessions. I'm sorry.
Yeah, so we can do all the questions and everything in this H tent. My colleagues are already there, and we'll do one final round of reading everybody's SIM cards who's interested, and then we'll do questions there too. Right? So H tent. So.